So first, let's look at an example. W equals ln x squared plus y squared plus z squared. And then these will in turn be given by, we'll have a curve, x equals cos t, y equals sine t, and z equals 4 root t. So first, we can find the derivatives, the partials of del w over del x, del w over del y, del w over del z. These are all going to be, so by the chain rule, we'll get 2x over x squared plus y squared plus z squared, 2y over x squared plus y squared plus z squared, and 2z over x squared plus y squared plus z squared. Then del x by del t, del y by del t, del z by del t. These will be negative sine t, cos t, and then this will be, I guess, 1 over 2 root t, or sorry, 2 over root t, rather. Right, and so now the chain rule will give that del w over del t, or I guess since now this is just one variable, we could even just write dw over dt. This will be negative 2x sine t over x squared plus y squared plus z squared plus 2y cos t plus 4z, all over x squared plus y squared plus z squared. This one is over, or z over root t. Now we can substitute in, so x squared plus y squared plus z squared, well, x squared plus y squared is equal to 1, and z squared is equal to 16t. So this will become all over 1 plus 16t, then the x, so this will become negative 2 cos t sine t plus 2 sine t cos t. So these will cancel out. And so we'll be left with just 4 z. So this will become 16 root t over root t. So eventually we get that dw over dt is just 16 over 1 plus 16t. Okay, now let's try to get that same result, but now writing things directly in terms of t rather than going through the chain rule. Erase this. So if we expand the definition, we expand the definition of w, we'll get w is equal to ln cos squared t plus sine squared of t plus 16t is equal to ln 1 plus 16t. And now by logarithmic differentiation, we see that, so d of ln is derivative of the inside thing, which is just 16, over the original thing, which is 1 plus 16t. And so it's a little more concrete. Let's evaluate this at a particular value. At t equals 3, dw over dt is 16 over 1 plus 16 times 3, which is 16 over 49. Next, let's do an example. Z is x squared minus y squared, and then x is u cos v, y is u sine v. So the partials of z, del z over del x, del z over del y, are 2x and negative 2y. Partials of del x by del u, del y, del x by del u, del y by del u, del x by del v, del y by del v. These are cos v, negative u sine v, sine v, and then u cos v. And so if we multiply these out, we'll get del z by del u, del z by del v. These will be, so 2x cos v minus 2y sine v, and I'll put a separator, and then negative 2xu sine v minus 2y u cos v. And now we substitute in the values, so x, this will be u cos 2u cos squared, y is u, so we'll get a sine squared. So this will become 2u cos squared v minus sine squared v, and this one will become u squared cos, and this will become u squared sine v. So we'll get, this will become negative 2 u squared cos v sine v. I'm sorry, it should be negative 4 since we've got two of them. Okay, so negative 4 u squared cos v sine v. Now let's again try to see that directly. So we expand the definition of z, we'll get, okay, z is equal to u squared cos squared v minus sine squared v. And now del z by del u, well, this part is a constant in terms of u, so we're just going to get, like, derivative of u is 2u, and then times this, cos squared v minus sine squared v, as we already got, and then del z by del v. Now the u is constant, or the u squared is constant. So this will be u squared, and then what's the derivative of this? One way to do this, you could rewrite this as, you could also do this using the product rule, but this is cos of 2v. So we could pull out the v by by the chain rule, and so then this would become u squared negative 2 sine 2v, and this is the same because sine 2v is the same as 2 sine v cos v. You also could have gotten that just using the product rule or the chain rule on each of these. So we get the same answer both ways. And again, let's evaluate this at some particular value to make this more concrete. So let's take at uv equals, let's say, 3 and then pi over 6. So cos squared pi over 6 is equal to, well, let's just do cos pi over 6 is root 3 over 2, and sine of pi over 6 is 1 over 2. So at uv equals 3 pi over 6, del z by del u will be 6 times 3/4 minus 1/4 is equal to 3. And del z by del v will be u squared. So negative 4u squared. Let's do it this way. So negative 4 times 9 times cos of u, or cos of pi over 6 times sine of pi over 6 times root 3 over 4, and so this will be negative 9 root 3. All right, now let's do an implicit differentiation example. This is going to be a little trickier. So we'll look at this x e to the y plus y e to the z plus 2 ln x minus 2 minus 3 ln 2 is equal to 0. So this defines an implicit surface. We want to find del z by del x, del z by del y at x, y, z equals 1 ln 2 ln 3. So this will look sort of confusing. I'm going to define a variable w equals x e to the y plus y e to the z plus 2 ln x minus 2 minus 3 ln 2. So the chain rule is going to tell us, so this will look kind of weird, but dw over dx, dw over dy will be equal to del w over del x, del w over del y, del w over del z, and then del x by del x, del y by del x, del z by del x by del y, del y by del y, del z by del y. So this is a little strange. What is the difference between this and this? So this we'll call the total derivative of w with respect to x. So let me just write down the partials of these. So I guess we can erase this since it's still up there. So the partial derivatives of w with respect to x are, the partial derivative of w with respect to x is e to the y plus 2 over x. The partial derivative of w with respect to y is x e to the y plus e to the z, and the partial of w with respect to z is just y e to the z. So that was for the variable w before we imposed equal to 0. Now, if we impose this equal to 0, then that implicitly, this will define z as an implicit function of x, y. So z equals h of x, y. And in that case, the inputs to w from x are not only coming from the variable x, they're also coming from the variable z. So dw by dx will account for the contributions to w coming directly from x, but also coming through z, which in turn is a function of x itself. Another way that might make this look less bizarre would be to introduce new variables and write x equals s, y equals t, z equals some function of s and t, and then here you would have dw by ds, dw by dt, and here you'd have still dw by del x, del w by del y, del w by del z. Okay, so in any case, this matrix is going to partials of x and y with respect to each other if these are independent variables. It's going to be 1, 0, 0, 1. And then if we're setting that, declaring this equation is equal to 0, then these total derivatives are going to be 0 as opposed to the partial derivatives. And so that is going to let us solve our problem. So that's going to give us, let's erase this. Okay, so this equation is now giving us that del w over del x plus del w over del z over del x is equal to 0, and likewise del w over del y plus del w over del z over del y is equal to 0. And so we solve del z over del x will be negative del w over del x, del w over del z, and del z by del y similarly will be negative del w by del y over del w by del z. So now we can evaluate that. Okay, so del z by del x will be negative e to the y plus 2 over x divided by y e to the z, and del z by del y will be negative x e to the y plus e to the z, again over y e to the z. And if we evaluate this here at 1, ln2, ln3, del z by del x will be that's negative 2 plus 2, so negative 4 over ln2 over 3 ln2, and del z by del y will be, that's negative, so the bottom is still 3 ln2, the top is 1 times 2 plus 3, so this will be negative 5 over 3 ln2.